So this was a sample problem we did not get to in class, so I'm going to walk through it now. But we did talk about polyprotic acids, and so just kind of generically we can write a polyprotic acid as being a species that might have more than one ionizable proton. So again, here I've written this as H3A. So the first dissociation, again in the presence of water, is going to generate H3O plus and then H2A minus. And we call this first dissociation Ka1, meaning the first ionizable proton to be released. What's going to happen after that is this substance, again still in the presence of water, will lose a second proton and will generate Ha2 minus. We call this acid dissociation Ka2. And then lastly, in the presence of water, we can have the third proton be released, generating A3 minus, and we refer to this guy as Ka3. So that's why when we have our table from Appendix 3 of equilibrium constants, right, we can see Ka1, Ka2, and Ka3 values. So something like acetic acid, for example, only has one ionizable proton. These hydrogen atoms don't come off in terms of acid-base chemistry. So we only see one equilibrium constant. However, for something like ascorbic acid, which is vitamin C, here we can see the chemical structure of that, it has more than one ionizable proton. Okay, and we can see those listed here, the two different ionization constants for that. So ascorbic acid is actually the species that we're looking at for this problem. So again, telling us that it's a diprotic acid, there's two ionizable protons, Ka1 and Ka2 are the equilibrium constants for them. And they want us to calculate the HASC concentrations, so they're abbreviating ascorbic acid as H2ASC. So this is from the first dissociation event and then the second dissociation event. So what we're going to do first to make sure that we understand this is just kind of write the two equations that are kind of relevant here and then talk about that. So we've got H2ASC. So that again is ascorbic acid, the diprotic acid. In the presence of water, we're going to have a proton get given up from ascorbic acid, generating the conjugate base, HSC minus. And we know that Ka1 for this is equal to H3O plus times HASC minus times H2ASC. And that's equal to the value that they gave us, which was 1 times 10 to the minus fifth. So this is the first dissociation. What really happens here, okay, is the second dissociation uses this same species as the starting material. So HASC minus, again in the presence of water, we'll have this species lose a proton and leave behind ASC 2 minus. Ka2 again being H3O plus, ASC 2 minus over HASC minus. And they give us the value of this guy as 5 times 10 to the minus 12th. So what we're going to do is we're going to treat this as just kind of a standard equilibrium problem. But what I'm going to show you is that after we consider the first acid dissociation event, the amount of this guy that we have is so small, because this is a weak acid, the amount of this guy that we have is so small that this second dissociation event, with a tiny teeny amount of this and a tiny teeny equilibrium constant, is going to be such that the amount of this guy that we make is basically negligible. What this does is, for most polyprotic acids, allows us to consider only the first acid dissociation event. So even though I wanted to make sure you understood the chemistry of what's going on here, this is so minimal in terms of its contribution to acid-base chemistry that we can basically, for all intents and purposes, ignore this in terms of our pH calculation. As we're going to see, we're not going to ignore it in terms of calculating this guy. All right, so let's go forward with kind of how we've treated these equilibrium problems. Write an equation, write your equilibrium expression, and make sure that the concentrations of species that you're going to use in your ICE table have the right units. And in this case, they tell us that we have a 0.050 molar solution. So that was given to us directly. We didn't need to do any further calculations. So I'm just going to rewrite our relevant equation down here so we can include it in our ICE table. So we've got 0.05. I'm going to lose some of this. Again, these ICE tables become pretty straightforward as we move forward here. So our Ka is going to be equal to 1.0 times 10 to the minus fifth, right? And it's going to be these species, which are our x, 0.05 minus x. Let's assume that x is small. Okay, we get x squared over 0.05. It's going to be equal to 1 times 10 to the minus fifth. Solve for x. X is equal to 7.1 times 10 to the minus fourth. And again, that equals our H3O plus concentration. Again, we're going to assume that when we have this as 7.1 times 10 to the minus fourth, and it slides so very, very little over, that this H3O plus concentration is negligible. Stop that, replay that, whatever you might need to hear that again, because that's important. If we consider the second equilibrium, we start with such a teeny amount of the acid, and it slides so very, very little to the right that the amount of H3O plus we'd make from that second acid dissociation is negligible. So we're going to consider all of the H3O plus concentration basically coming from this first dissociation. So pH being the negative log of that is going to give us pH equal to 3.15. So that answers this part of the equation. Okay, what's the pH? But it also asks us what's the HASC concentration and then the ASC2 minus concentration. And so for that, we're going to need to look at, well, we actually already know the HASC concentration. So the HASC concentration at equilibrium is equal to what our x was, which is 7.1 times 10 to the minus fourth. But what we need to do now to figure out the ASC2 minus concentration is use this second equilibrium expression. So Ka2 is equal to the H3O plus concentration times ASC2 minus over HASC. And we're going to use these values, which actually are going to be the same. So I'm going to walk through this, but hopefully this makes sense. H3O plus concentration that we figured out, right? Again, we talked about this equilibrium shifting so very little to the right, so that basically we're going to have the same HASC concentration that we had at equilibrium to start. So that's going to be 7.1 times 10 to the minus fourth. We said our H3O plus concentration is going to be 7.1 times 10 to the minus fourth. And what we want to solve for is our ASC2 minus concentration. We know that this is equal to Ka2. So hopefully you see that those cancel. And our ASC2 minus concentration is basically equal to the equilibrium constant. Now, if that was a little bit dicey for that second part, don't worry too much about that. But do understand that it is possible that I would give you a problem where you'd have to calculate the pH of a diprotic or a triprotic acid solution. But generally, we're only going to consider the first acid dissociation as being the major contributor to H3O plus concentration, and that's how we'd figure out pH. Last little thing we always want to do, we didn't do this, is we want to do a check. Make sure that we are valid in our assumption. So 7.1 times 10 to the minus fourth is our x. We are subtracting it from 0.05. Do our little check here, and that ends up equaling 1.4%. So we're okay.